Look up on a clear night and you might see it. A pale river of light spilled across the dark. It feels like a distant object, something over there, safely far away. But that feeling is the trap. The Milky Way is not a backdrop. It is the room you're standing in. Every direction you turn, you're looking through it, and the galaxy uses that fact to hide its shape like a magician hiding a card in plain sight. For most of human history, we stared straight at our own home and did not recognize it. Stay with me, and please like and subscribe. That soft band overhead is made of countless stars, so many that your eyes cannot separate them into points. You see glow instead of detail, a smeared brightness that looks almost painted onto the sky. Ancient people did what humans always do when faced with a mystery that refuses to explain itself. They gave it a story. The Greeks called it the Milky Circle. Romans imagined it as spilled divine milk. In China, it became the Silver River, a cosmic crossing that could carry legends as easily as it carried light. Those myths were not foolish. They were honest attempts to make meaning out of a pattern that offered no instructions. The Milky Way looks like a thing you can point to, as if it has a beginning and an end. It looks like a road, a scar, a veil. It does not look like what it really is, a vast rotating disk of stars, gas, dust and dark matter that we are embedded inside of right now, at this exact moment. Here is the paradox that haunted astronomy for centuries. To understand the galaxy, you want to step back and see the whole structure. But you cannot step back. You were born inside it. Everything you build, every telescope you lift, every camera you point is also inside it. Imagine trying to map an entire city while standing in the middle of a crowded intersection, with buildings blocking your view, headlights in your eyes, and street noise drowning out any sense of direction. You can measure nearby streets. You can guess where the center might be, but the skyline, the grid, the true shape of the city stays hidden. The Milky Way adds an extra layer of cruelty. Between us and the distant stars there is dust. Not the cozy dust under your bed, but fine grains spread through space that absorb and scatter visible light. Dust is the reason the galaxy can look bright and dreamy in one patch of sky, then suddenly vanish into darkness in another. It is also why the most important region, the center, is so difficult to study in ordinary starlight. The galaxy is like a library where most of the books are wrapped in black cloth, and you have to figure out the plot by touching the spines. So for thousands of years we lived with a sky that contained the answer, and still did not give it up. People could track planets, predict eclipses, measure seasons, build calendars, sail oceans, yet the Milky Way remained a kind of cosmic whisper. A presence, a texture, not a structure. The difference matters, because the moment you realize you're inside a structure, you stop treating the sky as decoration and start treating it like geography. That shift did not happen all at once. It took a new kind of curiosity and a new kind of stubbornness. It required someone willing to do boring work at an almost heroic scale night after night, not chasing comets or dramatic explosions, but simply counting. Counting stars. Counting them again. Counting them until the counts themselves started to draw a hidden outline. This is where the illusion starts to crack. If stars were scattered randomly, you would expect roughly similar numbers in all directions. Some variation, sure, but nothing systematic. Instead, the Milky Way cheats. When you look along that pale band, you see far more stars. When you look away from it, toward the darker regions above and below, the star numbers drop. That pattern is the first clue that the Milky Way is not a sphere around us, and not a flat painting on the sky. It is a flattened system, and we are looking through its thickest layer when we stare into the band. Even that simple statement is weird to feel in your bones. You're not looking at an object in space. You're looking through a slice of your own galaxy, edge on, like looking through the crowded length of a stadium rather than down onto its empty seats. The band is bright because it is packed. The darkness is dark because you're peering out of the main plane into a thinner region with fewer stars and sometimes less glow from gas. But the illusion fights back. Because we are inside a spiral arm, the galaxy does not present itself as a neat disk in the sky. It presents itself as a confusing overlap of distances. Near stars sit on top of far stars. Dust hides entire regions. Bright clouds mimic empty space by blocking light behind them. Two stars that look neighbours can be separated by thousands of light years, while two that look far apart can belong to the same structure, like beads on a wire seen from the wrong angle. So the first milestone of this story is not a picture, it is a perspective change. The Milky Way is not out there, it is around you. It is the environment your solar system moves through, the ocean your star swims in. That realization is small enough to fit in a sentence, yet big enough to rearrange your place in the universe. And once you accept it, another question appears immediately, sharper than the first. If we are inside the galaxy, then where inside it are we? Are we near the center or far out? Are we in a dense region or a quiet one? Are we safe where we are, or just lucky for now? These are not poetic questions. They determine how often nearby stars explode, how frequently radiation washes through our neighborhood, and how stable the long story of life can be. There is also a deeper emotional twist hiding in the science. The Milky Way becomes more mysterious, not less, when you learn what it is, because now you are not just admiring a beautiful sky. You are trying to understand a giant structure while trapped inside it, using light that can be blocked, bent, and delayed. You are doing archaeology with photons, reconstructing a history that spans billions of years, using clues scattered across distances your mind cannot naturally hold. Tonight, we are going to treat that pale band the way you would treat a locked door in your own house. Not as decoration, not as background, but as a challenge. We are going to find out how humans first discovered the Milky Way's shape from the inside, how our idea of the universe cracked open when Andromeda stopped being a smudge and became another galaxy, and why even now, with space telescopes and star maps of staggering precision, the Milky Way still keeps secrets older than Earth itself. Because the Milky Way illusion is not just a mistake we made long ago, it is a reminder that reality does not care what feels intuitive. The universe is under no obligation to make itself easy to understand from the vantage point of a single species on a small planet. And yet, somehow, we are learning to see. The first person to seriously crack the Milky Way illusion was not born into a modern laboratory, and he was not trained inside a university astronomy department. He was a musician. William Herschel made his living by performing and teaching, and by day his world was filled with instruments, scales, and careful listening. But at night he aimed that same obsessive attention upward, toward a sky that most people treated as scenery. It is hard to appreciate how bold that choice was. In the late 1700s, the night sky was not an endless catalogue of known objects. It was a frontier. Telescopes existed, but the best ones were rare, expensive, and limited. If you wanted a better view, you often had to build it yourself. Herschel did exactly that. He ground mirrors by hand, a slow, brutal craft where a mistake means starting over. It could take months to produce a single mirror good enough to focus starlight cleanly. He built instruments that were enormous for their time, with mirrors more than a foot across, far larger than anything most people had ever looked through. This was not romantic stargazing. It was labour, the kind that numbs your fingers and tests your patience. England at night can be cold and damp, and the work demanded long stretches of stillness. You press your eye to the eyepiece. You hold your breath. You try to convince your brain to distinguish faint points of light from the noise of your own vision. Then you count. 1, 2, 3. You write the number down by candlelight. You move the telescope a little. You count again, over and over, patch by patch, like surveying a continent through a straw. And Herschel did not do it alone. His sister Caroline worked alongside him, recording observations, doing calculations, keeping the project coherent when fatigue and frustration tried to pull it apart. Their partnership matters, because the Milky Way was not going to yield its shape to a single dramatic observation. It was going to yield it to persistence, to a mountain of small measurements stacked into a pattern. The central question they asked was deceptively simple. Are stars distributed evenly across the sky, or does their density change depending on where you look? If stars were scattered randomly, counts in different directions would not show a strong systematic difference. If the Milky Way was a real structure, a disk, a system with geometry, then the counts should reveal that geometry. So Herschel began a systematic survey. He pointed his telescope at regions along the Milky Way band and counted how many stars he could see. Then he pointed it away from the band above and below and counted again. He repeated this across the sky night after night, collecting numbers like a person collecting evidence for a trial. The pattern that emerged was revolutionary. In the direction of the Milky Way band, star counts surged. Away from it, they dropped. The sky was not uniform. It had a plane, a preferred direction, a thick, crowded belt. That belt was not just a pretty streak. It was the edge on view through a flattened system of stars. If you need an image, imagine a dinner plate sprinkled with grains of sand. Now place your eye inside the plate, somewhere near the surface, and look along the plane of the plate. Your line of sight passes through a lot of sand. It looks dense, it looks bright. Then look upward out of the plate. You see far fewer grains. That is the Milky Way effect. Herschel's star counts were the first real evidence that our collection of stars has a shape, a structure, and boundaries of a kind, even if we could not see them directly. This was a turning point. Before Herschel, the Milky Way was a mythic band. After Herschel, it was a physical system. Not a painting, but a place. Not a story, but an object that could be measured. The universe gained architecture. But there is a twist. And it is important because it shows you how science actually advances. Herschel's map was brilliant, and it was also wrong in key details. Not because he was careless, but because the galaxy was still lying to him in a more subtle way. Dust. The same dust that makes the Milky Way glow soft and uneven also blocks distant stars. When you count stars in a direction where dust is heavy, you see fewer, not because the galaxy ends there, but because the galaxy is hiding behind a curtain. Herschel assumed that where the counts dropped, the edge of the system must be nearer. That made the galaxy appear more centered on us than it really is. In a sense, the Milky Way used its own dust to forge an illusion of our importance. So Herschel revealed the disk, but he could not reveal the spiral. From inside, with visible light, and with dust in the way, the grand pattern remained concealed. He could sense the plate, but he could not see the swirl. Still, the achievement stands. Herschel changed the question from what is that glowing band to what kind of system are we living in? And that change opened the door to everything that came after. If the Milky Way is a structured system, then there might be other systems like it, other star cities, other disks, other spirals. At the time, this idea was still a whisper because telescopes could not yet settle the argument. Astronomers saw faint cloudy spirals scattered across the sky, and they did not know what they were. Some insisted they were nearby clouds inside our own system. Others suspected they were separate star systems at unimaginable distances, without a reliable way to measure those distances. The debate could go on forever. Herschel had given humanity its first real hint that the Milky Way is a disk seen from within, but the next leap would require a single number, a distance so large it would shatter the old universe and replace it with a far bigger one. And that number would come from a star that pulses like a heartbeat, steady enough to become a ruler for the cosmos. For a long time, astronomers lived with a strange compromise. They accepted that the Milky Way was a real system of stars, but they still did not know what the faint cloudy spirals in the sky actually were. Some looked like tiny whirlpools, delicate smudges with structure, as if the universe had scattered little ghosts of galaxies across the darkness. They were called spiral nebulae, and the name itself carried an assumption. A nebula is a cloud, meaning these spirals were probably just nearby gas inside our own Milky Way. But a few stubborn minds could not let go of a more unsettling possibility. What if those spirals were not clouds at all? What if they were entire star systems, as large as the Milky Way, sitting so far away that their billions of stars blurred into a single glowing patch? If that were true, then the Milky Way would stop being the whole universe and become just one neighborhood in something vastly larger. The debate sounds abstract until you realize what was at stake. This was not a minor detail about classification. This was the size of reality. It was the difference between living in the only city on Earth and discovering there are countless cities, each with its own lights, its own streets, its own history, scattered across distances that make the mind recoil. The problem was brutally practical. You cannot win an argument about distance without a way to measure distance. And in astronomy, distance is the hardest thing to measure because you cannot walk a ruler out to a star. You have to trick the universe into giving you a scale. You need an object whose true brightness is known, so that by comparing how bright it appears from Earth, you can infer how far away it must be. That is where a special kind of star enters the story quietly, like a metronome hidden inside the cosmos. Cepheid, variable stars pulse. They brighten and dim in a regular rhythm, and the crucial fact is that the rhythm is tied to the star's true brightness. A Cepheid that pulses more slowly is intrinsically brighter than one that pulses quickly. That relationship turns these stars into distance markers, the kind that can leap across the galaxy and keep working. In the early 1920s, Edwin Hubble was working at Mount Wilson Observatory in California, using what was then the most powerful telescope on Earth, the Hooker telescope. Its mirror was 100 inches across, a huge leap in light-gathering power for the time. Hubble pointed it at the Andromeda Nebula, one of the most famous of the spiral smudges, and he searched for Cepheid variables inside it. This was not easy work. The stars in Andromeda were faint, crowded, and easily confused with foreground stars from our own Milky Way. But eventually Hubble identified Cepheids and measured their pulsing periods. From those periods he inferred their true brightness. From the mismatch between true brightness and apparent brightness, he inferred distance. The number that came out of that calculation detonated the old universe. Andromeda was not a nearby cloud inside the Milky Way. It was far beyond the Milky Way. Hubble's original estimate put it on the order of about 1 million light-years away, already too distant to fit comfortably inside any reasonable Milky Way boundary. Later measurements refined the distance to about 2.5 million light-years, but the core conclusion never changed. Andromeda was a separate galaxy, an island of stars in its own right. In one stroke the sky doubled, then exploded outward. If Andromeda was another galaxy, then the universe was not a single star system with a few decorative clouds. It was a landscape of galaxies. Suddenly those other spirals were not oddities to be explained away. They were neighbours seen from an unimaginable distance. The Milky Way did not stop being important, but it lost its monopoly. We were no longer living in the whole, we were living in one example, and here is the delicious twist. The moment you accept that Andromeda is a spiral galaxy, you start to suspect something about your own home. If other spirals exist and we see them as spirals, then the Milky Way might be a spiral too. The glowing band across our sky might be the edge on view through the disk of a spiral galaxy, the same kind of structure we now see in Andromeda. But now the problem turns inside out. Seeing Andromeda as a spiral is easy because we are outside it. We get the postcard view. Seeing the Milky Way as a spiral is hard because we are trapped inside it. Dust blocks sightlines, star crowds confuse distance, and our own neighbourhood is not a neutral platform. It is part of the structure we are trying to map. So Hubble solved one mystery and created a deeper one. He proved galaxies exist beyond our own, and in doing so he forced astronomers to confront a new challenge. How do you prove the shape of your own galaxy when you cannot step outside it to take the picture? That challenge would define decades of astronomy. It would push scientists away from relying on visible light alone. It would inspire new instruments that listen to the galaxy in radio waves and see it in infrared. It would lead to space telescopes that pierce dust like fog lights, and to missions that track the motions of 1 billion stars as if the Milky Way itself were a living map. In other words, the universe did not just get bigger, it got harder. And the only way forward was to learn how to build a spiral from clues, from patterns, from patient reconstruction, like assembling a shattered vase when most of the pieces are hidden in the dark. Once Hubble proved Andromeda was another galaxy, the universe stopped being a single stage and became a whole theatre district. We could look outward and see spirals everywhere, graceful pinwheels of stars. But when we turned back toward our own home, the Milky Way refused to pose for the camera. It is a strange kind of irony. The farther galaxies are, the easier their shapes can be. The one we live inside is the hardest to draw. The obstacle is not a lack of effort. It is geometry mixed with dust. The Milky Way has lanes, layers, and crowded sightlines that overlap like reflections in a hall of mirrors. When you look toward the center, you are staring through thick regions of gas and dust that swallow visible light. When you look along the disk, you are looking through so many stars at so many distances that the sky becomes a pile-up of foreground and background. So astronomers had to switch tactics. If you cannot see the spiral arms directly in visible light, you look for clues that trace them. You search for objects that behave like neon signs nailed to the arms, things that are bright, young, and short-lived. You also search for signals that ignore dust, waves of light that slip through the murk the way a low bass note slips through a wall. Young stars became one of the first reliable breadcrumbs. The most massive newborn stars burn hot and blue, and they do not live long. In galactic terms, they are sparks. A few million years and they are gone, exploding as supernovae. That short lifetime matters because it means they die close to where they were born. They do not have time to wander far. If you map where the youngest bright stars are concentrated, you begin to trace the spiral pattern. Not perfectly, but enough to see that the Milky Way has arms and we are inside them. But the galaxy still keeps a deeper layer hidden. Stars are only part of the story. Spiral arms are also rivers of gas, and gas does something stars do not. Gas clouds can collide, compress, and light up in new wavelengths. Radio astronomy changed the game because radio waves can pass through dust that blocks visible light. With radio telescopes, astronomers could trace hydrogen gas across the Milky Way, including regions that were almost invisible in ordinary starlight. Hydrogen is the most common element in the galaxy, and it whispers at radio wavelengths in a way that is incredibly useful. By mapping hydrogen across the sky and measuring how its signal shifts as it moves, astronomers could infer where the gas is and how it flows around the galactic centre. It is like listening to traffic from a hilltop at night. You cannot see every car, but you can hear motion, density, and direction. Then came infrared. If dust is the problem, infrared is one of the best tools we have for slipping past it, because infrared light can penetrate dusty regions far better than visible light. The National Aeronautics and Space Administration Spitzer Space Telescope, launched in 2003, gave astronomers a way to see through much of the obscuring haze and detect stars that were previously hidden. Suddenly, parts of the galaxy that looked like blank space in visible light started to glow with structure in infrared, as if someone had turned on a lamp in a smoky room. But the biggest leap in the modern era came from something even more ambitious than seeing through dust. It came from measuring motion and position so precisely that the Milky Way could be reconstructed in 3 dimensions. The European Space Agency Gaia mission, which began operations in the early 2010s, has been measuring the positions and motions of more than 1 billion stars. Not just where they appear on the sky, but how they shift over time, how they drift, how they orbit. That sounds abstract until you feel what it means. Gaia is building a living map. It is using tiny changes in a star's apparent position, a technique called parallax, to estimate distance. It is tracking proper motion, the sideways drift of stars across our viewpoint, to see how different parts of the galaxy move. It is turning the Milky Way into a dynamic system you can study like weather patterns, not just a static picture you admire. From this mountain of data, a broad portrait emerges. The Milky Way is a spiral galaxy roughly 100,000 light-years across. But even here, the galaxy refuses to be simple. Astronomers still debate the exact number of major spiral arms. Depending on how you define an arm, you can argue for 4 major arms, or for 2 major arms with additional smaller structures that behave like partial arms. The argument is not petty. It reveals something profound about what spiral arms really are. Because spiral arms are not fixed objects, like the rigid spokes of a wheel. They are patterns. This is the part where the Milky Way gets weird in a way your intuition can actually grasp. Imagine you're driving on a highway and you hit a traffic jam. You crawl forward, then you speed up, then you're out of it. The jam itself seems to stay in the same region of road for a long time, even though the cars inside it are constantly changing. Cars enter the jam from behind, slow down, then leave at the front. The pattern persists even as the material inside the pattern flows through. Spiral arms can work like that. In the 1960s, astronomers C.C. Lin and Frank Hsu developed what is often called density wave theory. The basic idea is that the arms are regions where matter bunches up as it orbits the galactic center. The pattern rotates, but it can rotate more slowly than the stars themselves. Stars and gas drift into the denser region, slow slightly under extra gravity, and then drift out again. The arm is real, but it is real as a long-lived wave, not as a permanent pile of the same objects. And gas reacts dramatically when it enters one of these denser regions. It compresses. Compression triggers star formation. New stars ignite. The hottest newborn stars shine bright and blue, and because they die young, they light up the arms like fresh sparks along the wave. That is why spiral arms in many galaxies look bluish in photographs, while the regions between arms tend to look more yellow or red, dominated by older, longer-lived stars that have had time to drift away from where they were born. This also explains why mapping the arms is so hard from inside. You are not drawing the outline of a rigid structure. You're tracing a moving pattern in a flowing disk, where dust hides sections, where distance is difficult, and where the very definition of an arm depends on what you choose to track: gas, young stars, old stars, or the wave itself. So by the time you combine everything, young star clusters, hydrogen maps from radio telescopes, infrared surveys from space, and Gaia's three-dimensional motion map, you finally get something like an answer. The Milky Way is a spiral system, with a central bulge, a rotating disk, and arms that are both real and elusive, like long-lived ripples in a cosmic ocean. And now that we can see the spiral pattern more clearly, a new kind of question becomes unavoidable. If we live in a moving wave, where exactly are we riding it? What is our local address in this rotating city of stars? And what does that address mean for the history and safety of life on Earth? Once you accept that the Milky Way is a spiral, the next question stops being abstract and becomes almost uncomfortably personal. Where are you inside it? Not in a poetic sense, but as an actual address in a rotating system. If the galaxy is a city, then every star has a neighborhood. Every neighborhood has its own hazards, its own rhythms, its own long history of calm and catastrophe. And life on Earth has been shaped by where our sun happened to grow up. We do not live near the galactic center. We live out in the disk, tucked into a smaller structure called the Orion Spur, sometimes called the local arm. It is like a side street that branches between two larger highways of stars. On one side lies the Perseus arm. On the other side lies the Sagittarius arm. From the inside, it can feel like semantics, but this placement matters because the spiral arms are not just pretty. They are busy. They are where gas compresses, where new stars ignite, and where the most massive short-lived stars tend to be born and die violently. Those massive stars end their lives as supernovae, and supernovae are not gentle events. They flood nearby space with radiation and high-energy particles, and they can damage atmospheres over large distances. So the Orion Spur may have been a kind of quiet compromise, a safer lane in a galaxy that has plenty of dangerous neighborhoods. Not safe in an absolute sense, but safer than living deeper inside a major arm where the rate of stellar birth and death is higher. Now take a breath and let the next fact land properly. Your address is not stationary. The entire galaxy rotates, and it does not rotate like a solid record. Different regions orbit at different speeds. That is part of what keeps the spiral pattern alive, and it also means your local neighborhood is always on the move. Our sun takes roughly 225 to 250 million years to complete one orbit around the galactic center. Astronomers sometimes call this a galactic year, which is both a useful idea and a deeply unsettling one, because it shrinks the history of Earth into a handful of steps around a vast track. Think about the dinosaurs. The mass extinction that ended their reign happened about 65 million years ago. Since that moment, since the last of the great non-avian dinosaurs vanished, the sun has not even completed one full orbit. It has travelled only about a quarter of the way around the galaxy. We are still in roughly the same broad region of the Milky Way that the dinosaurs lived under, even though everything on Earth feels like it has been rewritten. Now zoom out again. Our solar system formed about 4.6 billion years ago. In that time, the sun has completed around 20 full orbits around the galactic center. 20 laps. That is the cosmic odometer reading of our entire planetary home. 20 times around since the sun first ignited and began turning hydrogen into helium, lighting the stage where life would eventually appear. And the speed of that motion is the kind of number that should feel illegal to your brain. The sun and everything gravitationally bound to it is moving at roughly 514,000 miles per hour as it orbits the galactic center. That is not a metaphor. That is your speed through the Milky Way right now. To get a grip on it, compare it to something your body understands. A commercial jet might cruise at a few hundred miles per hour. Our galactic orbital speed is roughly 700 times faster than that. At 514,000 miles per hour, you could circle Earth's equator in less than 3 minutes. And yet you feel nothing. No rushing wind, no sense of acceleration, no internal alarm that says you are moving at a speed that makes spacecraft look lazy. This is one of the most quietly mind-bending facts about living in the universe. Motion is not something you feel by itself. You feel changes in motion. You feel acceleration, not speed. The reason you do not feel our galactic orbit is the same reason you do not feel Earth's daily spin. Even though the surface at the equator moves at about 1,000 miles per hour, you, the ground, and the air are all moving together. When everything nearby shares the same motion, relative motion disappears. It's like being on a smooth train. If the ride is steady, you can forget you are moving at all. The Milky Way is doing that to us on a grand scale. The Earth orbits the Sun orbits the galaxy. Nearby stars orbit with us in a loose neighbourhood. Gas and dust share much of the same rotation. We are like dancers in a slow waltz, all turning together, and when you turn with the dance, the speed becomes invisible. But the galaxy still has one more trick. Our motion is not a flat, clean circle. The Sun also bobs up and down through the plane of the disk, oscillating above and below the midplane as it travels. One full up and down cycle takes roughly 60 to 70 million years. Right now, we are slightly above the midplane, moving upward. In about 10 million years, we will reach the peak of that vertical motion and then begin falling back down through the plane again. This is where science becomes a little spooky, because some researchers have wondered whether these passages through the denser midplane could be linked to long-term changes on Earth, more cosmic rays, more gravitational encounters with giant molecular clouds, more subtle nudges to the solar system that could increase comet disturbances or shift conditions over geologic time. The evidence for strong direct links is debated, and it should be treated carefully. But the idea itself is a reminder that the Milky Way is not a distant museum piece. It is an environment. It has weather, in a sense. Slow, immense, and sometimes violent. So our address in the Orion Spur is not just a place on a map. It is a moving trajectory through a living disk. A path that has carried Earth through quiet regions and past crowded ones, that has kept time on a scale where dinosaurs belong to a fraction of a lap, and where the rise of human civilization is a blink so small it barely counts as a step. And now that you know we are moving through the Milky Way like this, another question rises naturally out of the motion. If the disk is only the bright visible part, what is the larger structure we are really orbiting inside? Because the galaxy's gravity reaches far beyond the stars we can see, and at its heart sits something darker than dust. As you ride with the Sun through the disk, it is tempting to picture the Milky Way as a neat spiral plate, smooth and orderly, rotating in calm precision. But the real galaxy has edges that misbehave. It has layers you cannot see with your eyes, and it has old structures that hover above and below the bright disk, like ghosts of an earlier universe. Far beyond the familiar band, the Milky Way is surrounded by a halo, a vast three-dimensional region that contains some of the oldest stellar communities we know. These communities are called globular clusters. Each one is a dense swarm of hundreds of thousands of stars bound together like a drifting city. Many formed more than 13 billion years ago, back when the Milky Way itself was still assembling, when the universe was young enough that even the word history feels too small. Globular clusters do not sit politely in the disk. They orbit the galactic center on elongated paths that take them far above and far below the plane. Some plunge down through the disk, pass through its crowded traffic, then soar back into the halo again, like comets made of stars. In a way, they outline the galaxy's depth. They are a reminder that the Milky Way is not just a flat picture. It has thickness. It has a skeleton. And then there is the second surprise. Even the disk itself is not truly flat. From far away, many spiral galaxies look like clean rotating records. From inside, the Milky Way can trick you into the same assumption. But when astronomers started mapping the outer regions more carefully, they found a warp. The disk bends. Its outer edges curve up on one side and down on the other, as if someone gently twisted the brim of a hat. The farther from the center you go, the more pronounced this bending becomes. That warp is not just a cosmetic detail, it is a signature of forces acting on the galaxy over long spans of time. A perfectly isolated disk might settle into something smoother, but the Milky Way is not isolated. It lives in a crowded neighborhood of smaller companion galaxies, and gravity is a slow sculptor that never gets tired. Some of these companions are dwarf galaxies that orbit the Milky Way and gradually spiral inward. Some are so faint you would never notice them without modern surveys. But even when they are small, they still have mass, and mass tugs. Over millions and billions of years, repeated gravitational interactions can pull on the outer disk, bending it the way a steady hand can bend a flexible sheet without tearing it. There is something almost intimate about that idea. The Milky Way is enormous, yet it is not rigid. It responds, it flexes, it carries the memory of the past encounters in its shape. A warp is like a cigar that never fully heals, except this scar is tens of thousands of light years wide, and it gets stranger. The warp is not the only imperfection. The disk has ripples and waves, subtle patterns that suggest it has been disturbed, nudged, maybe even punched by events we are still working to reconstruct. Some of those disturbances may come from satellite galaxies passing through or near the disk. Some may come from the internal dynamics of the spiral pattern itself. The important point is that the Milky Way is not a frozen structure. It is a moving system with a history of impacts. So when you look up at that calm, pale band, you're not just seeing a stable home. You're seeing the bright surface of a complicated machine that has been shaped by collisions, mergers, and long gravitational negotiations. The disk is the part that shines, but the halo holds ancient relics. The warp hints at ongoing interactions. The whole system is still settling, still evolving, still being rewritten. This matters for one reason that goes beyond aesthetics. A galaxy's shape tells you how it has lived. A smooth disk suggests quiet growth. A warped disk suggests disturbance. A halo packed with globular clusters suggests ancient formation and early chaos. And when you combine these clues, you begin to sense something that is easy to forget. The Milky Way is old. It has been rotating for billions of years. It has consumed neighbours. It has been tugged and twisted by companions. It has built layers of structure that span far beyond what human eyes can see. And somewhere inside that layered system you are riding on a small star, in a minor spur, moving at an impossible speed, unaware because the motion is steady. Now imagine taking all of that complexity and compressing it inward toward the centre. Imagine the star density rising. Imagine orbits tightening. Imagine gravity becoming more intense until it stops behaving like a gentle pull and starts behaving like a trap. Because the disk and halo are only the outskirts of the real drama. The Milky Way has a heart, and that heart is crowded, dusty, and dominated by something we cannot see directly at all. If you have ever seen a photograph of the Milky Way taken from a dark desert, you have probably noticed that the band seems to swell into a brighter bulge in one direction. That is the galactic centre, the crowded core region where stars pile up by the millions. It looks bright in wide shots, almost inviting, but in reality, the centre is one of the hardest places in the sky to study in ordinary light. Dust blocks the view, and the density of stars makes everything overlap. It is like trying to study a fireworks show through fog while someone keeps turning on more lights behind the curtain. For decades, astronomers suspected that something massive was hiding there. Not a shining object, not a bright beacon, but an invisible weight. The clue came from motion. Stars near the centre were orbiting as if they were bound to a point in space that produced almost no light. They moved fast, too fast, their paths curved tightly around an unseen focus. Gravity was clearly at work, but the source of the gravity was not visible. That kind of behaviour can only be explained by something extreme. Either there was a dense cluster of dark objects packed into a tiny region, or there was a single compact monster with enormous mass, and the only way to decide was patience. You cannot watch a star complete an orbit around the galactic centre in a single night. You have to track it across years, sometimes across decades, measuring its position precisely enough that the curve of its path becomes a story. In the 1990s, two teams began doing exactly that. Reinhard Genzel and his colleagues, and Andrea Ghez and her team, launched a long observational campaign to track individual stars near the galactic centre. They used infrared techniques because infrared can slip through the dust far better than visible light. They needed adaptive optics, a way to counteract the blurring effect of Earth's atmosphere, so that the stars near the centre could be separated cleanly instead of melting into a single shimmering smear. Year after year, they watched the same stars move. And what they saw was astonishing. Some of those stars were not drifting slowly in huge orbits. They were whipping around the centre in tight ellipses. One of the most famous is known as S2. It completes an orbit in about 16 years. 16 years. Compare that to our Sun, which takes roughly 230 million years to orbit the galactic centre once. S2 is moving through its entire path in a time span you can follow within a human career. That fact alone is a signal flare. When an object completes a tight orbit in such a short time, it means it is held by an immense gravitational mass packed into a small region. The teams measured the orbit's size and speed, and from that they could infer the mass of the unseen object at the centre. The answer was not merely large, it was absurdly large. At the centre of the Milky Way sits a black hole with a mass about 4 million times the mass of our Sun. It is known as Sagittarius A star, named for the constellation Sagittarius where the centre appears in the sky. 4 million suns compressed into a region smaller than our solar system. A gravitational well so deep that once light crosses a boundary called the event horizon, it cannot return. No matter, no light, no information in any ordinary sense. The universe draws a line and beyond it the story ends from our point of view. It is difficult to truly feel what that means, so let us build a mental scale that your nervous system can understand. Imagine taking our Sun, that enormous burning sphere, and compressing it into something smaller than Earth. That alone is a black hole scenario. Now take that mass and multiply it 4 million times, then squeeze it into a region still smaller than the orbit of the outer planets. The centre of our galaxy is carrying a secret weight that could hold millions of suns. Yet it glows only faintly because the black hole itself emits no light. S2 made the black hole real because S2 behaves like a clock in a strong gravitational field. During its closest approach, S2 comes within a distance comparable to the scale of our outer solar system. At that point, its speed becomes mind-bending. Roughly 3% of the speed of light, translating to tens of millions of miles per hour. And when something moves that fast in a gravity field that intense, physics stops being a set of classroom equations and becomes something you can measure directly. Einstein's general relativity predicts that time runs slower in stronger gravity and at higher speeds. For S2 near its closest approach, that effect becomes detectable. Astronomers can measure how the light from the star shifts, stretched by gravity and by the star's velocity. They can watch relativistic effects unfold not as theory, but as observable reality. There is another eerie detail. When S2 swings through its closest point, its position on the sky changes noticeably from night to night. Not over centuries, not over a lifetime, over nights. That means astronomers can watch a star orbit a supermassive black hole in something close to real time. It is like seeing the gears of a cosmic machine turning. So the galactic centre became a laboratory, a place where we can test gravity under extreme conditions, a place where we can watch orbits precess, where the shape of the ellipse slowly rotates, matching predictions of relativity. Every careful measurement has reinforced the same conclusion: Sagittarius. A star is not a metaphor. It is an object with a measurable mass and a measurable influence that shapes the core of our galaxy. But the discovery also raises a deeper tension. If a supermassive black hole sits at the centre of the Milky Way, then our galaxy is not an exception. Observations of other galaxies suggest that many large galaxies have similar central black holes. That hints at a connection between black holes and galaxy formation itself. Did the black hole form first, seeding the galaxy around it? Or did the galaxy form first, feeding the black hole until it grew into a giant? We do not fully know. What we do know is that our galaxy's heart is dominated by something that is both invisible and immensely powerful. A silent object that shapes star orbits, influences gas flow, and has likely flared with violent energy in the past. And that leads to the next question. If a black hole emits no light, how can we ever truly see it? Not just infer it, not just weigh it through stellar motion. How do you photograph a darkness? A black hole is a rude object. It shapes everything around it. It drags stars into obedient orbits. It warps light itself, and then it refuses to show its face. By definition, it does not glow. If light cannot escape, then a normal telescope has nothing to catch. So the obvious question becomes almost philosophical. If the centre of our galaxy is dominated by Sagittarius A star, how do we ever see it at all? The answer is that you do not photograph the black hole, you photograph the last light that almost escaped. Near a black hole, gas and dust do not fall straight in like water down a drain. They spiral, they collide, they heat up. Friction and compression raise the temperature until the material glows fiercely in radio wavelengths. That glowing plasma forms a ring of light around the darkness, not because the black hole is shining, but because matter is being punished by gravity right up to the edge. If you could build a telescope with enough resolution, you could see a dark circular region where light is missing, surrounded by a bright ring where light is screaming. That dark region is the black hole's shadow, a silhouette carved into the glow of doomed material. The catch is resolution. Sagittarius. A star is huge in mass, but it is also far away, about 26,000 light-years from us. From Earth, its shadow is tiny on the sky. To resolve it, you would need a telescope that is effectively the size of our planet. So astronomers built one, not as a single instrument, but as a network. The Event Horizon Telescope collaboration linked radio observatories across the world, from mountain tops to deserts, spreading them across continents to create an Earth-size virtual telescope. Each site observed the same target at the same time, and their data was synchronized with extreme precision. Then the collaboration combined those signals using powerful computing to reconstruct an image, as if the separate dishes were pieces of one vast instrument. This is one of those moments in science that feels like it should not work, and yet it does. You take scattered fragments of a radio wave collected on different continents, you stitch them together with mathematics and patience, and you turn the whole Earth into a single eye. In 2022, they released the first image of Sagittarius A star's shadow. Not the black hole itself, but the evidence of it written in light. A dark circle surrounded by a glowing ring, a boundary between the visible and the unreachable. And here is a strange comfort. Sagittarius. A star looked remarkably similar to the other famous black hole image released earlier, the shadow of M87 star, which sits in a galaxy tens of millions of light-years away. Two different monsters, two different galaxies, and yet the same basic shape. Darkness framed by a ring of furious light. It is one of the clearest signs we have that black holes are not just theoretical solutions, they're real objects that follow consistent physical rules across the universe. But do not mistake that image for a portrait of stability. The gas around Sagittarius A star is not a quiet halo. It is turbulent. It flickers and shifts. It churns in magnetic fields. The ring in the reconstructed image is the result of combining data across time, turning a restless system into something you can hold still long enough to see. This brings us to an even more haunting fact. Sagittarius. A star is relatively quiet right now, at least compared to the blazing black holes at the centers of some galaxies. Some galactic cores shine like lighthouses, powered by black holes feeding aggressively and launching jets of radiation across space for millions of light-years. Our central black hole, by comparison, is more like a sleeping giant. It consumes little. It sits in the dust and waits. But the Milky Way keeps receipts, and the receipts suggest the giant has not always slept. Astronomers have found evidence that a few million years ago, the galactic center experienced a period of intense activity. Something likely fed Sagittarius A star. A gas cloud drifting too close, or a star torn apart, or a series of events that poured fuel into the black hole's region. When black holes feed, they do not just swallow, they convert a fraction of that infalling matter into energy, blasting radiation outward into the galaxy. The light from such an outburst does not simply vanish, it travels, and when it hits distant gas clouds, it can cause them to glow faintly, like a cave wall lit by a flashlight long after the person holding it walked away. Astronomers call these kinds of effects light echoes. They are one way to catch a glimpse of the past without having been there. Then there are the truly enormous structures that make the past hard to ignore. The Fermi Gamma Ray Space Telescope has detected vast lobes of high-energy emission extending above and below the galactic plane. They are called the Fermi Bubbles. Each one rises tens of thousands of light-years, like a pair of invisible chimneys built into the galaxy. Their exact origin is still debated, but the broad implication is difficult to escape. Something big happened at the center. Either Sagittarius A star flared, or intense star formation and supernova activity near the core helped inflate these structures, or both. The bubbles are not gentle. They are the footprint of energy released on a scale that rewrites the surrounding halo. This is the part where your relationship to the Milky Way quietly changes again. We tend to picture our galaxy as calm because it looks calm from Earth. The stars are fixed, the band is steady, the sky feels eternal, but the Fermi bubbles are a reminder that galaxies have moods. They can flare, They can blow winds. They can experience outbursts that leave scars visible across tens of thousands of light years. And here is the unsettling twist that makes the story feel alive. Sagittarius. A star could wake again. Not tomorrow, not in a way we can schedule, but in the sense that if enough material wanders too close, the black hole can shift from sipping to feeding. If that happens, the galactic center could brighten. Jets could form, radiation could surge. Earth would not be in immediate danger because we are far away in the disk, but the night sky could change in ways our ancestors would have found mythic. A brighter core, a new luminous presence where there is now only a faint bulge and a hidden shadow. So the first image of Sagittarius A star is not just a technical triumph, it is a psychological milestone. It is proof that the darkest object in our galaxy can still leave a visible signature if you build an instrument big enough and patient enough to catch it. But seeing the shadow only opens the next door, because the environment around the galactic center is not just extreme, it is strange. Stars crowd together, orbits tighten, encounters become common. Objects get flung outward at speeds that can throw them out of the galaxy entirely. The center is not just a place where gravity is strong. It is a place where the Milky Way behaves differently. If you could stand near the Milky Way's center, assuming you could survive the radiation and chaos, the sky would not feel like the one you know. It would feel overloaded. In our neighborhood, the nearest star is more than 4 light years away, and even on the darkest night you see only a few thousand stars with the naked eye. Near the galactic center, stars can pass within light days of each other. The density is millions of times higher than what we experience out here in the disk. That crowding changes everything. It turns the center into a place where gravity is not just a background force, it is an active social network. Stars tug on each other, orbits get perturbed, close encounters are common, some stars get slingshotted like stones from a sling. Delay flung outward at enormous speeds. These are called hypervelocity stars, and the name is not exaggeration. They can move fast enough to escape the Milky Way entirely, shooting out into intergalactic space. It is the ultimate eviction notice. One wrong gravitational encounter near the heart, and a star that spent billions of years inside the galaxy can be thrown into the long cold between galaxies, where the Milky Way becomes a shrinking spiral behind it. Hypervelocity stars are a clue that the center is not stubborn into where a calm disk orbit feels stable. It is a scattering chamber, a place where energy gets exchanged through close encounters, and where the black hole's influence turns orbital mechanics into something almost violent. Then there are the objects that refuse to behave the way we expect. One of the most fascinating examples is known as G2. It was first identified as a dusty gas cloud on a path that would bring it frighteningly close to Sagittarius A star. As it approached its closest pass in the early 2010s, astronomers watched with anticipation because the prediction seemed straightforward. A gas cloud passing near a supermassive black hole should be stretched, shredded, and fed into the darkness. It should trigger a burst of activity, a flare that telescopes could detect, but G2 did not cooperate. It survived the encounter largely intact. That was surprising enough to force a rethink. Maybe it was not just a gas cloud, maybe it contained a star at its core, wrapped in dust. Held together by its own gravity in a way a simple cloud would not be. The same observation produced 2 very different interpretations, and the center stayed weird. But the strangest puzzle is even more dramatic, because it challenges something basic about star formation. Near a supermassive black hole, tidal forces are intense. Gravity changes rapidly over short distances. That should make it difficult for a gas cloud to collapse gently into a star. You would expect the cloud to be pulled apart before it can settle into a stable contraction. Yet within about a light year of Sagittarius A star, astronomers have identified clusters of massive young stars. Some appear to be far more massive than the Sun, extremely bright, extremely hot, and most importantly, extremely young in cosmic terms. The question is simple and sharp, and how did those stars form there? There are a few leading ideas. One possibility is migration. The stars could have formed farther out in a less hostile environment, then gradually moved inward through gravitational interactions over time, like people drifting toward the city center. Another idea is that a dense disk of gas may have existed around Sagittarius A star in the past, briefly creating conditions where star formation could happen even under strong tidal forces. In that scenario, the center would have had an accretion disk, not just feeding the black hole, but also spawning stars before the gas was consumed or blown away. The truth might be a combination, or it might be something we have not modeled well enough yet. The galactic center is one of those regions where our physics works and still leaves gaps. We can predict the orbit of S2 with exquisite precision. We can image the black hole's shadow. We can trace gas and magnetic fields. And yet, when it comes to the birth of certain stars in that environment, the story is still unfinished. That is part of what makes the center so valuable. It is not just a monster in the middle, it is a test bench. A place where gravity, magnetism, radiation and turbulence collide, forcing our theories to either survive or evolve. And then there is a broader mystery that hangs over all of it. Sagittarius. A star is not just an object sitting at the center like a heavy stone. It may be tied to the entire life story of the Milky Way. Observations of other galaxies show correlations between the mass of the central black hole and the properties of the galactic bulge. Bigger bulges tend to host bigger black holes. That pattern suggests coevolution, a relationship where the black hole's growth affects the galaxy and the galaxy's growth affects the black hole. When a black hole feeds actively, it can release enormous energy. That energy can heat surrounding gas and even blow it outward, preventing it from falling in and also suppressing star formation in the central regions. In that sense, a black hole can act like a thermostat, regulating how much new star birth happens near the core. It is an odd concept. The darkest object can shape the brightness of the galaxy by controlling the gas supply. So the center is not just an extreme environment, it is a potential control knob for galactic evolution. But the Milky Way's story is not only written at the center. The outer regions carry another kind of violence, slower but just as real. Our galaxy is not a quiet island drifting alone. It is actively consuming smaller galaxies, ripping them apart and weaving their stars into its own structure. The proof is written across the sky in streams. Once you have seen the Milky Way as a structured spiral, it is tempting to picture it as a stable home, a grand rotating city that simply exists and spins. But that is not how large galaxies grow. The Milky Way is not just living in the universe, it is feeding in it. Right now, as you listen, our galaxy is tearing apart smaller galaxies that wandered too close, stripping them star by star and stitching their remains into its own body. The evidence is written across the sky in faint patterns that look like accidents until you know what they are. Astronomers have found stellar streams, long thin rivers of stars stretching in arcs around the Milky Way. These are not spiral arms, they do not fit the tidy disk. They are the shredded remains of dwarf galaxies, pulled apart by tidal forces, gravity acting like a slow, relentless rack. A small galaxy approaches, and the Milky Way's gravity stretches it. First the outskirts get pulled into trails, then the core loses coherence, and eventually the entire identity dissolves. This is not a metaphor. It is measurable. Stars in a stream move together in coordinated paths like a flock that remembers a direction long after the original nest is gone. For a long time we could only glimpse a few of these streams. They were too faint, too spread out, too easily confused with the background. Then a new kind of map arrived, and the Milky Way began confessing. The European Space Agency Gaia mission changed this story by turning star positions into star motions. Gaia is not just measuring where stars are, it measures how they move. That distinction is everything. A single star in the halo can look ordinary, but a million stars moving in a related way reveal structure you would never notice in a still image. Gaia exposed streams like hidden handwriting, not by making the stars brighter, but by showing that many of them share a common motion. When you start grouping stars by motion, the Milky Way stops looking like one clean system. It starts looking like a composite, like driftwood fused into a raft, like a city built on older ruins, with new streets laid over buried foundations. One of the most important discoveries in this area is often referred to as Gaia Enceladus, sometimes also called Gaia sausage, because of the elongated pattern its stars make in certain velocity plots. The name is strange, but the event it points to is not. It suggests that about 10 billion years ago, the Milky Way experienced a major merger with a dwarf galaxy. Not a tiny snack, but a serious collision in the Milky Way's youth. The basic signature is this. A large population of stars in our halo appears to share orbital and chemical traits that differ from typical disk stars. They move in ways that suggest they were not born in the Milky Way's thin disk. They were imported. The idea is that a dwarf galaxy fell in, was torn apart, and its stars were scattered through the halo, while the violence of the merger heated and thickened the Milky Way's disk. That word heated is doing a lot of work. It does not mean temperature in the normal sense. It means orbital chaos. A quiet disk has stars moving in fairly orderly paths close to the plane. A violent merger can pump energy into those orbits, kicking stars into higher and more tilted trajectories. Over time, this creates what astronomers call the thick disk, a layer of older stars above and below the thin disk where much of today's star formation happens. In other words, some of the Milky Way's structure may literally be the fossil of an ancient collision. The most unsettling part is the implication for identity. When you hear the word Milky Way, you imagine a single thing, a single object with a single origin story. But the streams and merger remnants suggest the Milky Way is more like a family tree, with branches grafted on through gravity. It is a quilt, not one cloth, but many pieces sewn together over billions of years. You can see this in chemistry as well as motion. Stars carry fingerprints of the gas they formed from. A star's spectrum, the way its light breaks into colours, reveals the presence of heavier elements. Astronomers often use the term metals for elements heavier than hydrogen and helium, and different galaxies enrich their gas at different rates. Smaller dwarf galaxies tend to form stars more slowly and lose gas more easily, so their stars often end up with different element ratios than stars born in a big well-fed spiral disk. That means the Milky Way contains immigrants you can identify, not by the look of a single star, but by combining its motion, its age, and its chemical fingerprint. This is why people sometimes call the field galactic archaeology. You're not digging with shovels, you're digging with data, reconstructing ancient collisions that happened before Earth existed, using stars as surviving artifacts. Once you start seeing the Milky Way this way, even familiar ideas feel different. The halo becomes less like a decorative glow and more like a graveyard of mergers. Some globular clusters may be relics brought in by swallowed galaxies. Some of the stars you see in the night sky may have been born in systems that no longer exist as independent galaxies at all. It raises a quiet, beautiful possibility. Our Sun may not be a native in the strictest sense. Even if it formed within the Milky Way's disk, the gas it formed from was enriched by earlier generations of stars, and some of that material may have come from galaxies the Milky Way consumed. In that sense, we are not just citizens of the Milky Way, we are descendants of lost galaxies. Our atoms may carry a history that includes homes that have been erased. And the cannibalism is not over. The Milky Way still has companions. Some are being stretched into streams right now, others are trailing gas like a wound through the sky. We are watching the process in slow motion, not as a distant theory, but as an ongoing event. So the Milky Way is not a peaceful island. It's a growing organism shaped by gravity, building itself by consumption. The next step is to look at the meals that are still on the table, the galaxies that are already bleeding seas and gas into our own. If you want to understand what galactic cannibalism looks like in the present tense, you do not need to imagine a sudden smash or a cinematic explosion. Most of the time it is quieter than that. It is slow-motion violence. A small galaxy falls into a larger one, and gravity does what gravity always does. It stretches, it strips, it rearranges. Over enough time, identity becomes a memory. One of the clearest examples is the Sagittarius dwarf galaxy. It is not a theoretical relic from 10 billion years ago. It is a neighbour in the process of being dismantled right now. As it orbits the Milky Way, each pass through the larger galaxy's gravitational field pulls stars away, peeling them off into long tidal streams. Those streams do not just trail behind like a tail, they wrap around the Milky Way, looping across huge arcs of the sky like ribbons wound around a spinning wheel. This is what makes the Sagittarius story so unsettling. The galaxy is not simply losing a few stars at the edges, it is being unmade. Its stars are being redistributed into our halo and our outskirts, diluted into a population that will one day look like it always belonged. If you fast forward far enough, no one will point and say that is Sagittarius. They will point and say that is the Milky Way. The meal becomes the body. The stream itself carries clues about the process. It is not uniform. Some parts are denser, some are thinner, and those variations encode an orbital history. Each wrap suggests another passage, another stripping, another round where gravity extracted more material. In a sense, the stream is a time record written in starlight. Not a sentence, not a plaque, but a trail that remembers where the dwarf galaxy has been. But stars are only half the story. If the Sagittarius dwarf shows you what happens to stellar populations, the Milky Way also has companions that show you what happens to the fuel of the future. In the southern sky, visible to the naked eye from dark places, sit two cloudy patches that do not look like individual stars at all. They look like detached pieces of the Milky Way, like someone tore a bit of the band loose and left it hanging nearby. These are the Large Magellanic Cloud and the Small Magellanic Cloud, dwarf galaxies orbiting our own. They are close enough that we can study them in exquisite detail, yet far enough that we can see them as whole systems. That combination is rare in astronomy, and it has made the Magellanic Clouds into some of the most important laboratories in the history of cosmic measurement. The Large Magellanic Cloud lies at a distance of roughly 160,000 light-years from us. The Small Magellanic Cloud is farther, roughly 200,000 light-years away. They are not just separate companions, they are gravitationally bound to each other as well, locked in a complex orbital dance while also feeling the Milky Way's pull. 3 bodies, 3 gravities, and a long argument written in motion. What makes them especially valuable is that they are not hidden behind the Milky Way's dense disk the way the galactic center is. We can look at them from the outside. We can see star-forming regions, star clusters, and the distribution of gas without the same level of confusion we face when mapping our own disk from within. Inside the Large Magellanic Cloud, there is a famous region called the Tarantula Nebula, one of the most active star-forming regions in our local group of galaxies. It is a reminder that dwarf galaxies can be small and still intensely alive. They can burn bright with new stars. They can forge heavy elements. They can run their own internal dramas. And yet, against the Milky Way, their fate is fragile, because the Magellanic Clouds are already leaking. Trailing behind them is an enormous ribbon of hydrogen gas known as the Magellanic Stream. You cannot see it with your eyes. You need radio observations to trace it. But once you know it is there, it changes your whole mental map of the sky. The stream stretches across an enormous fraction of the southern sky, like a giant invisible comet tail made of raw star fuel. It was first identified in the 1970s through radio observations, and it remains one of the largest structures associated with our galactic neighborhood. The stream contains enough gas to form huge numbers of new stars in the future. This is not poetic fuel. It is literal hydrogen, the base ingredient for star formation, being pulled away by gravity and scattered along an orbital path. The dramatic implication is simple. The Milky Way is not only consuming stars from smaller galaxies, it is also stealing their gas. It is draining the reservoirs that could have formed future generations of stars inside those dwarf galaxies, and it is redirecting that material into our own system. Every orbit, the Magellanic Clouds lose a bit more. Some of that gas will eventually fall into the Milky Way's disk. It will mix with our interstellar medium. It will compress in spiral density waves. It will become molecular clouds. And in those clouds, new stars will ignite, stars that will never know their gas once belonged to another galaxy. There is a strange tenderness to that, even though it is built on destruction. Galaxies do not just collide and erase, they also recycle. A stream is both a wound and a pipeline. It marks what is being lost, and it marks what is being gained. There is also an open question woven into this story, one that makes the present tense even more intriguing. Some measurements suggest the Magellanic Clouds may be on their first close approach to the Milky Way, having fallen inward from farther out over cosmic time. If that is true, then we are watching the beginning of a long relationship, not the final act. The bleeding has started early, and the merger itself may still be billions of years away. So when you look at the Milky Way as a calm band of light, remember the hidden scaffolding around it. There are streams of stars that are the remains of dwarfs being dismantled. There are rivers of gas stretching across the sky, feeding future star birth. The galaxy is growing not by simple accumulation, but by transformation, by taking other systems apart and folding them into itself. And there is a final irony that sits quietly behind all of this. The Milky Way can consume smaller neighbors for a long time, but it is not the last predator in the neighborhood. Someday something its own size arrives. For most of your life, the word galaxy probably feels like a permanent noun. The Milky Way, Andromeda. Two grand objects hanging in space as if they were carved and placed there. But galaxies are not carved. They are drifting, rotating and responding to gravity the way water responds to a slow tilt. Over enough time, even the largest structures do not stay politely separated. Andromeda is the nearest large spiral galaxy to our own, and it is not standing still. It is approaching. The distance is enormous, on the order of a couple million light years, which is why the approach feels meaningless in daily life. But in cosmic time, the approach is a scheduled event written into the math of gravity. Current models suggest that in about 4.5 billion years, the Milky Way and Andromeda will collide, not as a single dramatic impact, but as a long drawn-out dance that spans millions of years. The first thing to understand is what will not happen, because your instincts will try to sabotage the picture. Two galaxies contain hundreds of billions of stars each. You might imagine a catastrophe of star crashing into star, worlds shattering, everything turning into fireworks. But space inside galaxies is absurdly empty. Stars are tiny compared to the distances between them. Even in the densest parts of a disk, the average spacing is so vast that direct stellar collisions are rare. So the galaxies will pass through each other, and most stars will not hit anything at all. But that does not mean nothing happens. Gravity does not need contact to be violent. Gravity reaches out, reshapes orbits, and rearranges structure. During the first close pass, the gravitational pull of each galaxy will tug on the other's spiral arms, stretching them outward into long streamers of stars. These tidal tails can extend for hundreds of thousands of light years, creating huge arcs of light that would look like luminous ribbons in a night sky. If there is any civilization alive in either galaxy at the time, their view will be beyond anything we can easily imagine. Andromeda will not be a faint smudge. It will swell into a vast, bright presence across the sky, a second Milky Way growing larger over generations, until it becomes an overwhelming structure with detailed dust lanes and star clouds visible to the naked eye. Stars will mostly slip past each other, gas will not. Gas clouds have size, they have volume, they collide and compress. When the Milky Way and Andromeda interpenetrate, their gas reservoirs will slam together in places, triggering enormous bursts of star formation. Cold gas will compress into dense knots. Those knots will collapse. New stars will ignite in great clusters, and many of those newborn stars will be massive, short-lived and violent. In other words, the collision will light up both galaxies with new starbirth, not because stars are crashing, but because gas is being squeezed. After the first pass, the galaxies will not simply merge instantly. They will swing apart again, pulled by their momentum like two dancers who clasp hands too tightly and then spin away. But they will remain gravitationally bound. Each close encounter robs the system of orbital energy through complex gravitational interactions, and each time they separate, they do not separate as far as before. Over time they fall back together, then they pass again, then again, a series of collisions rather than one. With each pass, the old spiral order is shredded. Orbits become scrambled. Stars get flung into new trajectories. Some will be tossed outward so far that they drift into intergalactic space, becoming lone travelers in the dark. Others will be drawn inward toward the combined center of mass, feeding the growth of a more rounded central structure. Eventually, after repeated passes and enough time for gravity to mix everything, the two galaxies will settle into a single merged system, likely more elliptical than spiral. The graceful arms that define the Milky Way today will dissolve into a smoother distribution of stars, a big diffuse glow rather than a pinwheel. Some astronomers have even given this future remnant a playful nickname, blending Milky Way and Andromeda into one word. The joke is light, but the outcome is serious. A galaxy can lose its identity and become something new, not by being destroyed, but by being transformed. Now add one more layer of cosmic irony. The timeline of this merger overlaps with the future of our own sun. About 4.5 billion years from now, the sun will be moving into its late life phases, swelling into a red giant. It will expand dramatically, and its changing luminosity will reshape the inner solar system. Earth, if it still exists as a recognizable world, will face an environment very different from anything life has ever known. So there is a strange symmetry. The galaxy that gave birth to our solar system will be changing form at the same time our star is changing form. The larger home and the local home will both be in transition. None of this is meant to be a doomsday story. It is a scale story. The universe moves. The structures you think of as stable are stable only on the timescales of a human life. On billion-year timescales, even common galaxies behave like weather patterns, drifting, colliding, and reorganizing under gravity's patient rules. And there is something quietly comforting in that. A collision between galaxies is not chaos in the sense of randomness. It is chaos in the sense of complexity, a system so rich that you cannot predict every detail, yet still governed by consistent physical laws. The stars will follow gravity. The gas will follow pressure and turbulence and magnetic fields. New stars will light up where compression happens. The final remnant will settle where energy can no longer keep the two systems apart. So the Milky Way is not just eating small neighbours, it is also destined to meet an equal. And here is the thing the collision story sets up, like a shadow behind the bright drama. We talk about the Milky Way as if it's mostly made of stars. But when you start calculating how galaxies behave in collisions and how fast they rotate and how they hold together, you find a disturbing mismatch. The mass you can see is not enough. Something unseen is doing most of the gravitational work. If you could somehow weigh the Milky Way, not just the bright stars you can see, but every planet, every cloud of gas, every ember of dust, every black hole, every drifting rock, you would expect the math to close neatly. Gravity should match the mass. Motion should match the gravity. The galaxy should behave like an honest machine. But it does not. The deeper astronomers measured how the Milky Way and other spiral galaxies rotate, the more unsettling the result became. There simply is not enough visible matter to explain the way galaxies move, not even close. The stars you see, the glowing disk, the gas we can detect in radio and infrared, all of it together appears to make up less than about 15% of the Milky Way's mass. The rest is missing from our senses, and yet that missing mass is clearly doing something, because the galaxy stays together. The first hints of this problem emerged far from the Milky Way in the 1930s, when a Swiss astronomer named Fritz Zwicky studied clusters of galaxies. He measured how fast galaxies were moving inside those clusters and found a contradiction. The galaxies were moving so quickly that given the visible mass, the clusters should have flown apart long ago. Something unseen had to be adding extra gravity, like invisible rebar holding a crumbling structure together. For a while, the idea sat in the shadows, not because it was silly, but because it was inconvenient. Physics does not like invisible ingredients. Then, in the 1970s, Vera Rubin pushed the mystery into the spotlight with an observation that was too clean to ignore. She studied how spiral galaxies rotate, measuring the speeds of stars at different distances from the galactic center. Your intuition, trained by the solar system, expects one pattern. Farther out means slower. Mercury orbits quickly. Neptune crawls along because the sun's gravity weakens with distance. But Rubin saw something different. In galaxy after galaxy, the rotation curve stayed flat. Stars far from the center were moving almost as fast as stars much closer in. According to the visible matter, those outer stars should not be moving that quickly. They should be drifting in weaker orbits or escaping into intergalactic space. Instead, they kept circling as if the galaxy had a huge hidden mass extending far beyond the bright disk. This is the point where the Milky Way stops being just a spiral of starlight and becomes something more like foam on a dark ocean. The visible galaxy, the part that shines, appears to be embedded in a massive halo of unseen matter that reaches far outward. For the Milky Way, models based on the motions of stars and satellite galaxies suggest this halo may extend hundreds of thousands of light years across, far larger than the bright disk that spans about 100,000 light years. In other words, the Milky Way's true body is mostly invisible. The stars are the ornamentation on a much larger gravitational structure. Astronomers call this unseen mass dark matter. The name is honest and slightly annoying. Honest because it does not glow or absorb light in the way normal matter does. Annoying because it sounds like a substance we already understand, like a darker kind of dust or gas. It is not that. Dark matter does not behave like ordinary atoms. It does not clump into stars, does not form planets, does not make chemistry. As far as we can tell, it mostly just sits there creating gravity. And that raises a brutal question. What is it made of? We can say with confidence what it is probably not. It is probably not ordinary gas or dust, because ordinary matter interacts with light and would reveal itself somewhere across the electromagnetic spectrum. It is probably not just a halo of hidden normal stars, because those stars would still shine. It is probably not mostly black holes, because large populations of them would leave detectable gravitational signatures in the way they bend light. So the leading explanations move into the world of particles we have not yet directly seen. One long-running candidate is something called weakly interacting massive particles, hypothetical particles that would have mass but would almost never collide with ordinary matter. Another candidate is axions, extremely light particles proposed for a different reason in particle physics that could also account for dark matter if they exist in vast numbers. These ideas are strange, but they are not fantasy. They are testable, and scientists have been trying to test them for decades. The experiments are quiet, patient, and almost absurd in their care. If dark matter barely interacts with normal matter, then any detector on the surface of Earth is flooded with false signals from cosmic rays. So researchers build detectors deep underground, under mountains, in mines, beneath thick layers of rock that act like a shield. Some experiments use ultra-pure liquid xenon, watching for tiny flashes of light that would occur if a dark matter particle hit a xenon nucleus. Others use crystals cooled to extreme temperatures, searching for minuscule vibrations or heat from a rare collision. The dream is simple. If dark matter particles are passing through Earth like an invisible wind, then once in a great while, one of them should tap a nucleus in the detector. A faint signal, a tiny knock on the door. Enough knocks, and you can infer what is knocking. So far, the door has stayed stubbornly quiet. There have been hints and disputed signals, but no detection has held up across different experiments with enough certainty to declare victory. That silence is frustrating, but it is also information. It could mean the particles interact even more weakly than expected. It could mean the particle mass is outside the ranges many detectors were optimized for, or it could mean we are hunting the wrong kind of beast. And whenever a mystery refuses to be caught directly, people do what scientists always do. They consider whether the mystery is not a new thing in the universe, but a mistake in our understanding of the laws. One alternative family of ideas modifies gravity itself, suggesting that at extremely low accelerations, like those at the outskirts of galaxies, gravity behaves differently than the classical laws predict. The most famous version is called modified Newtonian dynamics. It can reproduce flat rotation curves in many cases without invoking dark matter, which is appealing because it keeps the universe from having to invent an invisible substance. But modified gravity struggles with other evidence, especially on the scale of galaxy clusters and in the patterns of the cosmic microwave background, the ancient afterglow of the early universe. Many lines of observation point toward the same uncomfortable conclusion. There appears to be about 5 times as much dark matter in the universe as ordinary matter, and it plays a crucial role in shaping the cosmic web that galaxies form within. This is why missions like the European Space Agency Euclid Telescope and the upcoming Nancy Grace Roman Space Telescope matter so much. By mapping how mass bends light from distant galaxies, a phenomenon called gravitational lensing, these missions help trace the distribution of dark matter across huge volumes of space, but they do not solve what dark matter is, but they show where it must be. So here is where we end up, and it is both humbling and weirdly intimate. Most of the Milky Way is not the stars you see. It is an invisible gravitational structure that holds the spiral together, guides the motion of galaxies, and shapes the large-scale architecture of the universe. And right now, as you sit there, that unseen component is passing through you, through your walls, through the ground beneath you. You cannot feel it because it does not push on your atoms the way normal matter does, but it helps hold the galaxy that holds you, which means the Milky Way has not one hidden layer, but at least 2. Dark matter as the invisible halo, and another invisible system inside the visible disk itself, a web of gas, dust, magnetic fields, and energetic particles filling the space between stars. If the dark matter halo is the galaxy's unseen foundation, then the next layer is its unseen bloodstream. When you look up at the Milky Way on a clear night, it is easy to think you are seeing a solid thing, a dense stripe of stars painted across the sky. But most of the galaxy is not stars. Most of the galaxy is space, and that space is not empty. It is filled with an invisible ecosystem, a thin, restless mixture of gas, gold dust, magnetic fields, and high-energy particles that stretches across the disk like a nervous system. Astronomers call it the interstellar medium, and the name almost understates what it does. It is the raw material of future stars. It is the recycling bin of dead ones. It is the place where the chemistry of life begins before any planet exists. Even though it is incredibly diffuse, far more tenuous than any vacuum we can create on Earth, the interstellar medium still contains a significant fraction of the galaxy's visible mass, on the order of 10 to 15%. Spread over the vast volume of the disk, it is thin, but collected into clouds, and it becomes powerful. The interstellar medium comes in phases, like a weather system operating on cosmic scales. There are cold molecular clouds, dense and dark, where temperatures can be only a few tens of degrees above absolute zero. These clouds are star nurseries. Gravity can slowly gather their gas, pulling it into denser clumps until collapse begins and new stars ignite. There are warmer regions of gas heated by nearby stars glowing faintly in infrared and radio, and there are hot regions blasted by supernova explosions, gas heated to millions of degrees that shines in X-rays. These phases flow into each other. Gas cools and condenses. Gas gets heated and expands. Shockwaves ripple through it. The galaxy is not a static sculpture. It is a circulating atmosphere. But the interstellar medium is not just a soup of atoms. It is threaded with magnetic fields, invisible lines of force that stretch across light years. These fields shape how charged particles move. They guide flows. They influence how gas clouds collapse. They can slow star formation by providing pressure that resists gravity until gravity finally wins. How do you map a magnetic field you cannot see? One method is surprisingly elegant. Dust grains in space can align with magnetic fields, and as starlight passes through those aligned grains, the light becomes slightly polarized, its orientation subtly changed. By measuring that polarization across the sky, astronomers can infer the direction of magnetic fields throughout large regions of the galaxy. The result is startling. The fields are not random. They often follow the spiral structure, reinforcing the sense that the Milky Way has an underlying invisible architecture that helps shape the visible one. Then there are the travelers. The interstellar medium is filled with cosmic rays, high-energy particles accelerated to near light speed by supernova shocks and other violent events. Thousands of them pass through you each second unnoticed. They are tiny bullets of energy, and the galaxy's magnetic field acts like a maze for them, bending their paths and trapping many of them within the disk for long spans of time. Cosmic rays are not just a curiosity, they drive chemistry. When they collide with molecules inside cold clouds, they can trigger reactions that would not happen in peaceful conditions. Over time, the interstellar medium becomes a chemical factory. Radio telescopes have detected more than 200 different kinds of molecules drifting through interstellar space. Water, ammonia, alcohols, complex carbon chains, even molecules that hint at the building blocks of amino acids. The raw ingredients of biology do not begin on planets. They begin in darkness between stars, in cold clouds where chemistry is slow but persistent. This changes the story of life in a subtle but profound way. Earth is not an isolated miracle assembled from scratch. The solar system formed from a cloud that was already enriched, already chemically active. When the sun ignited about 4.6 billion years ago, it formed inside a molecular cloud that contained not just hydrogen and helium, but heavy elements forged by earlier stars and complex molecules built in the interstellar medium. The oceans, the carbon in living things, the nitrogen in your DNA, they come from a supply chain that began long before Earth existed. And the supply chain is powered by death. When massive stars die as supernovae, they blast heavy elements back into the interstellar medium. Carbon, oxygen, silicon, iron. They also send shockwaves that compress nearby gas, triggering new star formation. In that sense, supernovae are both destroyers and creators. They end a star's story and seed the next generation. Over time, this produces a galactic recycling loop. Gas becomes stars. Stars fuse light elements into heavier ones. Stars die and return enriched material to space. That material cools into clouds. Clouds collapse into new stars and planets. The cycle repeats. The galaxy renews itself. Some of the most dramatic evidence of this cycling appears in large hollow structures called super bubbles. When many massive stars form together in a region, they often die together within a few million years. Their supernova explosions overlap. Their winds combine. The result can carve a cavity hundreds of light years across, surrounded by shells of compressed gas. These shells can glow in radio and X-rays, and they can trigger star formation at their edges, like a wave pushing material into a ridge. Even the Milky Way's halo participates. Hot gas from supernovae can rise above the disk, driven upward by energy. As it cools, it can fall back down, raining onto the disk as cooler clouds. Astronomers call this the galactic fountain. It is a circulation system that helps mix heavy elements across large regions over long time spans. This is why the Milky Way is not simply a collection of stars orbiting in a vacuum. It is a dynamic ecosystem, a living environment where matter moves through phases, where energy and magnetism shape behavior, and where the seeds of future stars and future planets drift invisibly between the bright points. If dark matter is the galaxy's unseen foundation, the interstellar medium is its unseen metabolism. And now we arrive at one of the most profound tensions in the entire story. If the galaxy is full of raw materials, full of stars, full of planets, and if planets are common, then the Milky Way should be fertile not just for chemistry but for life. Modern discoveries suggest that most stars have planets. Many planets orbit in zones where liquid water could exist. The numbers get so large that your intuition breaks. Tens of billions of potentially Earth-like worlds in the Milky Way alone is not a crazy estimate. It is the kind of number that makes loneliness feel statistically unlikely. And yet, when we listen, the galaxy is silent. So the final question is not about structure, or motion, or dark matter, or gas. It is about company. With all these worlds, with all this time, where is everybody? The more we learn about the Milky Way, the harder it becomes to accept the quiet. A spiral galaxy with hundreds of billions of stars should not feel empty. Planets are not rare decorations, they are common. Many stars have them. Many systems have several. Some of those worlds sit at distances where temperatures could allow liquid water, and water is the great solvent of chemistry, the stage where complex reactions can keep running long enough for something like life to emerge. That is the trap. Once the numbers get large enough, your mind starts expecting company. Modern planet hunting has made this expectation sharper. When NASA's Kepler Space Telescope watched thousands of stars for tiny dips in brightness, it revealed a simple truth that still feels new. Planets are everywhere, not just gas giants, small rocky worlds too. The exact count of Earth-like planets in the Milky Way is uncertain, because our instruments have limits, and our definitions get slippery. But the broad message is difficult to dodge. Even conservative estimates imply an enormous number of potentially habitable worlds in our single galaxy. So why is the Milky Way so quiet? This question is often called the Fermi paradox, named after physicist Enrico Fermi, who famously asked a blunt version of it during a casual conversation. Where is everybody? If intelligent life is common, if technological civilizations are likely, if the galaxy is old and wide and full of opportunities, then we might expect evidence. Signals, probes, megastructures, even accidents, something. Instead, we mostly hear static. For decades, researchers have been listening through projects like the Search for Extraterrestrial Intelligence, scanning the sky for narrow radio signals that would stand out against natural noise. Modern efforts like Breakthrough Listen have expanded that search using powerful telescopes and huge computing resources. The logic is straightforward. Nature makes lots of messy signals, but certain kinds of patterns are hard to produce without intention. A narrow band radio tone, for example, is one of the simplest markers of technology. So far, no confirmed signal has survived scrutiny as an undeniable message from another civilization. There have been intriguing candidates, but nothing that holds up across independent checks. That silence can mean many things, and each possibility changes the emotional meaning of the universe. One possibility is that life itself is rare. Not microbial life, which might appear easily in the right conditions, but complex life. The kind that becomes ecosystems, the kind that invents tools, the kind that builds radio transmitters and wonders who else is out there. Complex life may require a chain of good luck so long and so specific that it almost never completes. A stable star, a protective magnetic field, a planet that keeps its water, a history that avoids sterilizing catastrophes for long enough. Maybe Earth really did win a cosmic lottery. Another possibility is darker. The galaxy could be full of life and still full of cannibalism because technological civilizations do not last long. This idea is sometimes called the Great Filter, somewhere between lifeless chemistry and a civilization that spreads through the galaxy. There is a barrier most attempts do not cross. The filter could be behind us, meaning the steps we already took were incredibly unlikely. Or it could be ahead of us, meaning many civilizations reach our stage and then collapse through war, environmental failure, runaway technology, or risks we have not even learned to name yet. There is also a gentler possibility that still feels eerie. Maybe civilizations are out there, but they are quiet on purpose. They could be observing younger worlds without interfering, like a cosmic wildlife preserve. People sometimes call this the zoo hypothesis. It is speculation, but it fits the silence in a way that is emotionally unsettling. It turns the galaxy into a room where you are talking loudly while others listen behind the walls. Then there is the most mundane possibility, which is often the most underestimated. Timing. The galaxy is vast, but the speed of light is still slow when the distances are measured in tens of thousands of light years. A civilization could broadcast for a few centuries, then go quiet, and its signal would be a thin shell expanding through space. If that shell never passes Earth during the short window when we are listening, we miss it entirely. Two civilizations could exist in the same galaxy and never overlap in time, and signal in a way that allows contact. We might also be listening in the wrong way. Radio is a technology, not a law of nature. Civilizations might communicate using methods we have not learned to detect effectively, or they might have moved beyond broadcast signals because broadcast is inefficient and loud. A species that becomes cautious might stop shouting into space, so the silence does not prove we are alone, but it also does not comfort us with company. What it does is force us to look inward at what we are, because even if the galaxy is silent, it is not indifferent to our existence in a simple way. We are made out of it. The atoms in your body were forged by the Milky Way's long history. Hydrogen is ancient, born in the early universe. Carbon was cooked inside earlier stars. Oxygen was forged in stellar cores and scattered by explosions. Iron was made in catastrophic deaths of massive stars. Some of the heaviest elements on Earth were likely created in rare collisions between the densest stellar remnants. None of that is poetry. It is supply chain. You are not standing outside the story of the galaxy. You are one of the galaxy's patterns. A temporary arrangement of old atoms that learned how to look up and ask questions. The Milky Way built 1 billion stars, then built planets around many of them, then in at least one place, built a mind that can map the spiral it lives inside. If we are alone, then consciousness may be one of the rarest things the universe has done. That would make it precious in a way that is hard to put into ordinary words. The Milky Way would be mostly unobserved, a great turning machine without anyone inside it to notice the turning except us. If we are not alone, then the silence is not an empty room. It is a waiting room, a place where contact is possible, and the first proof might arrive as a faint pattern hidden in noise, a thin whisper that changes everything. Either way, the Milky Way remains what it has always been, a spiral of starlight wrapped around invisible mass, filled with gas and magnetic fields and chemical ambition, rotating slowly through the dark. It has secrets we have solved and secrets we have not even learned how to ask. It has a shadow at its center. It has scars in its halo. It has rivers of stolen stars. It has a future collision written into gravity, and it has you. So when you look up at that pale band, remember that it is not just scenery. It is your origin. It is your environment. It is the larger body that has been carrying your world through space the whole time you have been alive and long before. The galaxy turns, the night changes, the questions remain. And somewhere in all that quiet, we keep listening, because curiosity is what the Milky Way looks like when it becomes aware of itself.